I welcome all of you to my module CG5031 Chemical Engineering Design Methods. My name is Vasant. I will be your lecturer for this particular module. And then what we're going to learn in this module is we're going to learn two different software. One will be Aspen HYSYS and another one will be Dynachem. And I will be covering this part Aspen HYSYS in a very detailed fashion. Then probably Matthias Van Dijk, he will cover the Dynachem. I think he will teach you the Dynachem part. And for the final exam, it will be you will get roughly 80 percentage of your marks from Aspen HYSYS. You are going to do a very big project, and then remaining 20 percentage will come from Dynachem. Probably we may alter the scoring, probably 70 from Aspen HYSYS and 30 from Dynachem. So we will tell to this probably in the week 3 how we are going to grade this particular module. So, and how I'm going to teach this is maybe for this lecture, lecture 1 and lecture 2, I'm going to use paper tube, which you are watching at the moment. So I will write everything that I want to say in a smart notebook, so it will be transformed, or that you can, whatever I'm going to write in the smart notebook, you can see that in the screen. So normally what I do is I talk and then I write, but normally it takes a lot of time. So if I write 2 page and if I also talk during that time, it will take roughly, I don't know, maybe 15 to 20 minutes. So what I did is I almost gave the lecture. So I talked to myself, I wrote everything that I want to say. So which means I already wrote whatever I'm going to talk in this lecture. So I'm going to use my written notes, and then I will use that notes to deliver this particular lecture. So that's how you are going to see for lecture 1 and also for lecture 2. And from lecture 3, you are going to see the software. I'm going to show you a few things in the Aspen HYSYS software. And then you are going to repeat the exercise. And what we are going to learn through from this module, especially from my part, which is Aspen HYSYS. So what I'm going to do is there are many ways to study Aspen HYSYS. So one way is to stick to the internet resources. In fact, the company Aspen Tech, they themselves posted loads of videos in YouTube which you can watch and then you can learn. I learned it through that way. Obviously, we also have very good textbooks to learn Aspen HYSYS, and most of them are available online. And then we also have some books in our library. You can take the book, you can just follow the book, and then you can come to the lab, sit in front of computer, and then solve the exercise one by one. That way you can learn. Yeah. So normally, so I'm handling this module for the last 2 years. And normally what I do is I give a tutorial book, and then we solve like a basic unit operation, for example, like a simple pump or a compressor, something like that. And then we will go to the different unit operations, like for example a continuous third tank reactor, and then we go to a slightly bit more complex topic like absorption column, distillation columns, and so on. But so what I'm going to do, and and, and I got few feedbacks from the students from last year, and they are not really great, because what I do is I solve those simple unit operations, especially single unit operations, and then I ask them to give me submit a project report, which is something like a mini design project, if you want. You can call it it's not even a mini, it will be like a mini design project, yeah, something like a manufacturing of say like acrylic acid, and they have to they have to come up with a design idea, and then they have to use an Aspen HYSYS and then build the process flow sheet using the software, and probably students were not enjoying it. So what I did this time is I'm going to do the tough part and you are going to do the easy part. So the tough part is I'm going to make a full plant, a chemical engine, like a full plant. And I selected manufacturing of vinyl chloride monomer. So I'm going to show how to how to get this product. And it's like we will see what are the chemical reactions involved and what are the reactants involved, how they react, what are the products that we get, at what conditions we get this product, what are the different unit operations involved. And also it's not just we are producing this product, so we are going to make near to 100% purity, so 99.5 percentage purity of a vinyl chloride monomer. So this is something like a like a very big process flow sheet. Normally uh, it will take a lot of time if you do it by yourself. So what I'm going to do is like I will do this tough part, and then once we learn this, you can use the book which I'm going to give you, and then you can do the easy part, like simulating a simple pump or simulating a simple compressor, and or maybe simulating a like single unit operation, for example absorption tower, maybe like a distillation column, for example. So you will practice that by yourself, or maybe obviously I will help you whenever you have some problem. But in this uh, but I will begin with the, the toughest part, yeah? It may look a bit tough at the beginning, especially the moment we are going to use the Aspen Plus software. You may you may think it may be difficult, but once you start to practice, then it will become easy. So what I recommend you is listen to these first two lectures carefully, line by line, word by word. Take notes, whatever you think which is important to consider, and then from the third lecture you watch the video like from minute 0 to end of the video. Probably I will put maybe lecture 3, lecture 4, lecture 5. So I will try to split the videos, and then so you watch all of them, and then you come to the lab. Obviously I will help you how to to use the software, but before entering the lab you have to see all these videos, and then try to repeat the exercise, and then you will think, and if you repeat the exercise one time or maybe twice, then I'm 100% sure you will 100% sure that you will get familiarized with this software. So I'm not sure whether this is the right way to approach, but if you have some feedback, obviously you can write me through email, or you can even come to my office. I will email you where is my office and how to contact me and what time I'm available. So what we will do is we are going to do a mini final year design project. In fact, we can remove that word mini. In fact, it's almost equivalent to your final year design project, but we are going to do it in Aspen HYSYS. Obviously, your final design project, you have to do it manually. You have to show the calculations, how it's done, and the assumptions and the rationale behind all the assumptions that you are going to make. But for the moment, you will we will do the final something almost a final year design project using Aspen HYSYS, and obviously we are going to do it together. That's why we will have a lot of tutorial sessions for this particular module. And then just to follow my pen, let me change it to highlighter. Where is that? Okay, just follow the green highlighter. So what we are going to do in the you will do in the final year will be will be engaged with some design project. It will be designing your chemical process. So for that, what you will need is you will design some major unit operation, and then some minor unit operation, and obviously you will perform a lot of heavy duty chemical engineering design calculations. So obviously, if you manage to do the design project, which mean you can call yourself as a hardcore chemical engineer. So, and even this module, the especially Aspen HYSYS is a hardcore chemical engineering subject. Yeah? So the software is extremely user friendly. It's if you know to use the mouse, you can it's then you can easily drag and drop the unit operations. You will learn that very soon from lecture 3. But to to deal with the software, you should be a pure chemical engineer. You have to apply a lot of chemical engineering concepts. It's not only a software, It's also to, okay, it is a software, and it has a very nice graphical user interface, but it will also test your limit, or it will also test the knowledge, chemical engineering knowledge in particular. So if you don't know some basics, the basics of the chemical engineering unit operations, then you are going to have a big disadvantage in this module. Yeah. So, but anyway, don't panic, because I'm going to show almost all the unit operations through this one big exercise. So you will learn it bit by bit. Even if you don't know, you still have time to learn it. So let's go to the next page. So when I said, like, normally for design project we need chemical engineering knowledge, and also for Aspen HYSYS we need a bit of chemical engineering knowledge. So what do I mean by this chemical engineering knowledge? Like, you should have a knowledge on mass balance. Obviously, I'm sure you know how to perform this, and also a bit of energy balance, and you should be good in reaction kinetics and engineering. So always remember in your mind. So all these chemical engineering knowledge are the subjects which I'm listed here. You would need this really for your final year design projects. But for Aspen HYSYS, the overall general concept, or the or the or the general picture about mass balance, energy balance, reaction kinetics is more than enough. Yeah? The software will do the calculations for you, and then heat transfer, and obviously sizing and costing analysis. So in fact, Aspen HYSYS can do all of this unit, all of these calculations for you. Like, it can perform mass balance, energy balance, and obviously you have to supply. You have to supply, for example, some expression that can describe the reaction kinetics involved in the main process. So that's all under this topic. And then whenever I say like final year design project, obviously you will know that in the next semester. But the title may look something like this. So manufacturing of some commodity chemicals, for example. So, and in this model, as I said, we are going to do something exactly similar, manufacturing of vinyl chloride monomer. Yeah. We will come back to that later in bit more detailed way. But for the moment, this lecture is going to be more like like a general introduction, what we are going to do, what we are going to learn, and how we are going to approach this module, and what are the things you should know before we go into the software and so on. Yeah? And then you have to remember, like like what we are going to learn and how we are going to learn. That's also important. So we are not going to use the software to design some new processes, so keep this out of your mind. So what we are going to do is, like, we are going to simulate the full chemical engineering plant, or a plant, maybe you can say chemical plant, using Aspen HYSYS. So say like vinyl chloride monomer, that's the one I'm going to show to you. It's a it's an existing process, and if you just Google it, you will see, yeah, different type of like um, like many people work on this particular project, both academic people like university researchers, and also industries. You can also find a lot of patents in Google patents. You can check them. So so this is like a well understood process. So we know at what temperature what happens, and what type of catalyst we need to use in order to get a desired product. And we also know from the literature, like if you dig into the literature, we know, okay, these are the reactions involved, these are the temperature we need. At this temperature the reaction proceeds forward, and some all of your reactants get converted into product. And obviously you need to purify that product. To purify this product, you need few more unit operations, like say for example pyrolysis. I need a liquid extractor, I need an absorption column, I need a distillation column, in order to get 100% pure product, and so on. So this is like well understood process, and well established process. And we are going to, and there are many ways to manufacture this product. So we will select maybe one particular way to manufacture this product, and then we are going to simulate the full plant using Aspen HYSYS. So These first two lectures, it may look a bit boring, and you may think we are going a bit slow, but it's better to learn this module step by step, very slowly, because it's okay. Aspen HYSYS is a software. It can reduce your workload, but at the same time, you also need a hardcore chemical engineering skill, and also you didn't develop the software. I didn't develop the software, so it's a commercial package. So especially when we have some error, or when the calculation goes wrong, so that's the time you need to really have your chemical engineering skill. Yeah. So, and also obviously you are going to get a lot of error. When I tried to simulate the whole process in my computer, obviously I got error in almost every step which I am trying to do. So which means, so that's okay. Yeah, if you get error, which means you are trying something, and if you are fixing the error, if you manage to fix the error, then you are really a chemical engineer, because you know how to fix the error, which means you know what's the problem. Something is happening in the process, some parameters are missing, so you know what are the parameters are missing, or you know what are the required parameters in order to make the simulation to to converge you. So this is something that you are going to learn a bit by bit, and something that I want to to recommend you. I recommend you to follow the lectures very carefully. Don't skip the video. Obviously, there are few lectures that you can skip the video of, like okay, minute one, and then skip and then go to the step two, and then skip and then go to the step three. Don't skip the videos like that. Okay, you can skip the videos in lecture one and two. Uh, although I don't advise you that, but from lecture three, the moment we start to use the Aspen HYSYS, don't skip the video. Just follow it. Remember, you don't have to remember the steps, but you have to understand the procedures. Yeah. So even if you are bored, please do not skip. So that's the only advice I have for you for this particular module. It's not a bad advice. Okay. And then we will design a chemical plant. I will try to design manufacturing of a vinyl chloride monomer, and then if we really have time, I can do one more example for you. Probably we don't need it. Huh? So, but if you are still struggling, I can show you one more plant for you. So as I said, we will select one process which is well understood, and then this is something like a note that I want you to keep it in your mind. So designing something new technology or protocol that allows to manufacture a new product. So we are not going to do that. We shouldn't do that using Aspen HYSYS. So because Aspen HYSYS need a lot of information, like how, what type of reaction kinetics, or expression that governs that particular chemical reaction, or at what temperature you can separate your uh, your fluid mixture. Say like your fluid mixture contains A and B, and you say like if you're using a distillation column at that particular temperature, at that particular pressure, you get something in the top, you get something in the bottom. So you should have some knowledge about fluid properties, and so on. And you will also learn in this particular module, like what type of information that we need, or just imagine like if I ask you to design, say manufacturing of a vinyl chloride monomer, and I ask you to, okay, come up with some process flow sheet that allows you to manufacture this particular product, and use Aspen HYSYS to simulate, then what type of literature you have to, or what type of information you need, or what type of information you need to look in the literature. Obviously you can get plenty of information in the literature, but still you should know what type of information that we are looking for. Yeah? So, so this is something that you will learn through this module, and this is really important. This is going to give mm, give you a big advantage in your final year design project. So that's why I said that don't skip anything. So I will show how to search few things in the literature, and we will take some values from the literature while we are going to simulate the whole process. Yeah? And then even if you're going to simulate a particular unit operation, say for example a simple CSTR where some chemical reaction is happening and we need to simulate that, so what type of information that we need, so those things that we are going to learn from this module. Yeah, from lecture 3, when I'm going to show how to connect the unit operations and then how to build the entire process flow sheet, you will learn all of these things step by step, line by line. Yeah? So just put some examples. If you take a continuous stir tank reactor where we perform the main reaction, so and then so if you want to simulate this particular process CSTR, then what are the information that we need? And then for example distillation column, obviously we need temperature, pressure, and something like a number of trays, and what's your feed stage. So so where your feed enters in which stage, so this type of information you need. If you take simple absorption, you need to know flow rate and also the properties of your absorbent, and also say temperature, pressure, and also the few more information that you need in order to design an absorption unit. So by the way, this distillation and absorption are purification techniques. Normally we perform the main reaction in the continuous stirred tank reactor, so where we convert our reactants into products, and obviously our product may not be 100% pure, and if we need 100% purity, then obviously we need to go for some other operations like distillation, absorption, filtration, and so on. So if you are going to simulate the other unit operations, you need to know a lot of information. Yeah, only then you can rely on the software. Yeah? So your software won't give you every information like, oh, you are going to manufacture vinyl chloride monomer. So if you just connect the unit operation, it's not going to solve it by itself. You have to give the right level of information. So that's why we call you as chemical engineers, and you should know what type of information we should supply. Even if you don't know, that's okay, we are going to learn that in this module. And then say for example a plug flow reactor or maybe a heterogeneous catalytic reactor, again we need to worry about reaction kinetics and what type of kinetic expressions that we need in order to simulate a heterogeneous catalytic reaction. Yeah. And coming back to CSTR, again, we need to worry about reaction kinetics. What type of reaction? Is it a first order? Is it a second order? Which type of reaction uh, can can explain how fast your reactants are getting converted into products? Yeah? And we will learn how to, okay, obviously if you go to literature, you can get information. Okay, a plus b goes to c, and this is the reaction rate, and the reaction rate follows some first order expression, and these are the first order kinetic constant, and so on. This type of information you can get it in the literature, and obviously you have to implement in Aspen HYSYS. Yeah? So you take that information from the book or from the literature, and then we are going to Aspen HYSYS. We are going to load that information as one of the input while we are going to simulate the process. Yeah. So this is few more points. So what we are going to learn a bit more. So how to open the software? This is something that we are going to learn, and then what it can do, and then how to feed the information, and more importantly, how to feed the right information. Yeah. So so if you provide the wrong information, obviously you cannot get the right output, and sometimes your simulation will not even converge. Yeah. So you will get a lot of errors, and which means you have a lot of job to fix later after that. And then I will also show you how to add some specifications, like for example fluid properties, like if you're using some, say like for example carbon dioxide or hydrogen, you you should know like the there should be some mathematical model that should accurately predict that fluid property. So we will come back to that later, that you will learn by doing this or solving the, the problem, or when you use the software, you will learn even bit more. Yeah. So, and then obviously you will learn how to implement reaction kinetics, and obviously how to, whenever I say some specification, it involves this fluid properties, your reaction kinetics. Just follow the green highlighter, and then your process conditions, like say like at what temperature and pressure you are performing that particular unit operation. It can be a reaction, it can be distillation, absorption, extraction, anything that you can name. Yeah. And also some rationale. Yeah. So uh, when we are going to design some particular process, we need to convince the, you need to, first you should convince yourself, okay, these are the, these are the particular reason I selected this particular process in order to produce that particular product at that particular experimental condition. So you should have some particular reason behind that. Yeah? So there is no point in manufacturing a product, say like if you manufacture a product A for say 10 euro, and if manufacture the same product for 100 euros, obviously I will go for the the economically viable option. You know, something that can manufacture, that allows you to manufacture the product at cheaper cost. And sometimes I will also think about the safety. Yeah? Like if you can manage a process, if you can manage to manufacture your product at a much at moderate conditions, I can say like that, like a moderate temperature, moderate pressure. So you will learn about this when we are going to talk about distillation. Like example, if you take a distillation, like distillation is is economic only at some particular range of pressure and temperature. So this is something that you will learn through the example which I am going to solve for you. Yeah. So these are the things you should keep it in the mind. So these are the things I call it as a rational. And then we, and obviously in the final year design project, this is what I understood. The students, they have to convince us, like like why you selected those processes. We will give something like okay, manufacturing of a citric acid. There are so many ways to manufacture citric acid. So you have to come up with a reason, like okay, I checked in the literature, in the textbook, in the patents, we see this so many number of processes, but I'm convinced this is the process I'm going to select for this and that and this and reason, that reason. So this is something you have to know. Yeah? So as a chemical engineer, it is a must. So we cannot pick randomly, like okay, today is Friday, so I go for process one. No, you shouldn't do that. Huh? So you have to to apply your chemical engineering brain before selecting the process. And this rule doesn't apply for the whole process. This rule apply even for a single unit operation. Yeah. So if I'm going to perform a distillation column, I prefer to perform my temperature within the range 25 to 185 degrees centigrade. That is the reason for that. So you have to keep these things in your mind as a chemical engineer, and then you are going to design those particular unit operation, or maybe the full plant which you are going to do. Yeah. I'm going a bit slow, but it's okay to go slow for this module. Yeah. And then obviously you're going to learn how to add unit operations. Yeah. Obviously, if you want to manufacture your product, you cannot do everything in one unit operation like a CSTR. No, you do the reaction, and then you need to purify it. You may need to go for a distillation, you may need to go for absorption, you may need to go for extraction. So many things comes on, or maybe you may even need to burn some product. So in that case, you may need a pyrolysis chamber, or maybe you you need some catalyst, for example. So so that you are something like so that you can speed up the reaction. So there are so many things involved, which mean you may need more than one unit operation. We will learn how to add different unit operations in a particular fashion, and then how to connect them, and then how to define the inputs in each of those unit operations, what type of information are required in each of those unit operations, and how to give the right type, right inputs. So like say you start the process with say like 10 degrees centigrade, but when we go to the purification stage, you need your all the streams to be at say 100 degrees centigrade. Why is that? These are the reasons that we are going to discuss when you are going to design the full plant. So this is something that you're going to learn through this module. And then obviously how to perform mass balance, energy balance, I'm not going to say it because the software is going to do it, but I will show like what the software will do and where to get those numbers, from the process flow sheet. And obviously we can do the sizing calculations. And then, as I said, I like to take this module very slow. So we will cover these topics step by step in a very detailed fashion. So if you if you follow these lectures, then you are going to have a very big advantage in your final year design project. So this is something you are going to probably you may repeat whatever we are going to do. This is what something you're going to repeat probably for other type of systems. Like Mm, let's begin by defining process simulation. I don't know what I wrote. Okay, yeah. So before we touch the software, I want you to know what is a process simulation is, because this is what that you are going to do using the software. I just wrote it. There is nothing big to explain here. So just read it. So it's a something like a representation of a chemical process by a mathematical model, which is then solved to obtain information about the performance of a chemical process. So just put if you take a simple CSTR, so what we are going to do is like we are going to simulate the CSTR. Let's call it a CSTR, and it will have some mathematical model. We need to load the correct type of mathematical model and then the correct inputs that allow us to predict the output. And the same rule apply for a distillation column. Yeah. Something like some feed goes in at that particular temperature, say some particular pressure, some particular composition, say it contains two components, x and y. We get x in the top, y in the bottom. So what will be your condenser temperature and pressure? What will be the reboiler temperature and pressure? So these are the information that we need, and there will be some mathematical equation or some model if you want, that allows you to calculate all these informations precisely. And whatever the things which is happening here, that that's something we call it as a process simulation. So we are practically simulating a process. uh, you give some you take a process, you give the right level of mathematics, you use the correct mathematical model, and then you give the right input and we get the right product. Yeah, so something like that. And if we want, I think I can change the highlighter to a normal pen. Let's take the pink color. So sometimes this process modeling is also known as process flow sheeting. So process flow sheeting is defined as the like say like what we are going to do. That's nothing but a process flow sheeting. So we are going to use some computer aids to perform steady state heat and mass balance calculation, sizing and costing calculations for a chemical process, or or maybe for a full plant. Yeah. So we will come back to that later. Yeah? And then what's the purpose of process design? This is really important. So the whole purpose or the aim of process design is to predict how a defined process would actually behave under a given set of operating conditions. So this is something that is there is nothing to explain great in this, like so we we know say for example a continuous tank reactor, and then you give some input and then we change the some conditions, and then we want to know what will be the output may look like. So this is something we are going to simulate as a function of operating variables, or we can call it as operating variables and also operating conditions. So operating variable, I mean like if you change a flow rate, what happens to your product concentration and so on. So anyway, I wrote it in a bit detail in the next 2 pages, so you will understand at the end of this lecture what the process simulation can do. So what will be our aim? So our aim is to predict the output of the process when the process flow sheet and its inputs are given. So I just draw some images here. So you so this is just for an example. Yeah. So just assume that this is your main process. Say it's a CSTR tank where your reactants B and A are getting converted into product. Say we have C in the exit stream, and then it goes to some process 1, and then it goes to some process 2, process 3, process 4, and then the final output we get a purified product of C. Yeah, and this process 2, it may be converting your one of your product again back into C, and then here we may be purifying. Yeah, we are separating the different components in the product, some impurities in the product, and then finally we get a purified product. Yeah, so this is your whole process flow sheet will look like, but we need to we need to give the right level of information. Yeah, so for the main process we need to provide the right mathematical model. We also need to give the right flow rate, and we also need to tell the right operating conditions like temperature and pressure. For example, there are many reactions it can move forward only at a particular temperature. Yeah? So we need to know what type of process it is. Is it an exothermic reaction? Is it an endothermic reaction? Is it a first order kinetics? And so on. Yeah? So these are the things that you need to know. And obviously, the same rule apply for process 1, process 2. So what type of temperature we need in order to separate two components from their mixture. Yeah? So using some particular unit operation. So that's like a general flowchart, and now we can see a slightly sophisticated example. This is a simple CSTR. So we have two reactants, so A and B. So it enters your CSTR, and then you take the product C. So just assume we are performing some reaction, and assume we are performing in a continuous mode. So which means the flow rate of C that should be equal to the flow rate of A plus flow rate of B. Yeah, so this is something in a continuous mode. So and we can also assume the process already reached the steady state conditions, which means the process at the moment is at steady state. And then obviously this is a continuous process. Say this, and this is a chemical reaction. Say A plus B gives C. So obviously your percentage conversion of A to C, so time versus percentage conversion, for example, just to follow the pink color pen which I'm writing at the moment. So yes, as a function of temperature, your conversion is going to to change. This is one example, and also as a function of other operating conditions, your percentage conversion is going to change. For example, your percentage conversion can be altered by altering the feed flow rate. So assume your volume of your continuous state tank reactor is constant. Then if you change the flow rate, your percentage conversion will change. So if your flow rate is low, probably you get 80 percentage conversion, and if your flow rate is high, you may get something less than 80 percentage conversion. So these are the that's why I said you should have some chemical engineering knowledge. So you might have learned this already in your reaction engineering. And then say like for example, if you want to know how the percentage conversion will change with respect to flow rate, this is something that we can simulate using the Aspen HYSYS software. And this is the concept of a process simulation. So if you have the so we need to have a right model that allows you to give an answer for this. Okay, this is my reaction, and I have the right mathematical model, and now I want to see how my conversion changes with respect to flow rate. So this is a process simulation. So that's the one of the idea behind process simulation. Now, I want to, I have some idea. I have already worked on what type of models that I need to use, and I know this. I know this is my feed condition. So now I want to know the the percentage conversion, which is related to your output. Or maybe we can do something else. So for the same problem, let's assume the flow rate remains constant. Yeah. And then now we change the reactor volume. Again, obviously the conversion will change. So why is that so? This is something that we that you will know from your from chemical engineering basics. Yeah. So obviously if you change the flow rate, if your volume is constant, if you change the flow rate, which means you are changing your residence time. And if your residence time decreases, your percentage conversion decreases. Yeah. And if your residence time increases, your percentage conversion increases. So if your flow rate is constant and if your volume is bigger, which means obviously your residence time of your reactants in the unit volume of reactor will be high, which means your percentage conversion will be more. So that's what I said it here. The answer is residence time of the reactants in the unit volume of the reactor. So if you want, we can calculate the residence time. It's easy if you know the volume and if you know the flow rate. So that will give you a residence time. So what do I mean by process simulation? So at the moment we are talking about CSTR. So with respect to CSTR, if you need to simulate the process, say for example, mm, let me change it to highlighter for a second. Follow the red highlighter, maybe the pink highlighter. So just to follow the highlighter. So for the moment, say like I want to know how the percentage conversion changes as a function of flow rate. So if you plot something like a flow rate on the x-axis, say like 10 ml per minute, 20 ml per minute, 30 ml per minute, and 60 ml per minute on the x-axis, and then your percentage conversion on the y-axis, 0% conversion to 100% conversion. So, and assume volume is constant. So, and if you really simulate your process, you may get some curve like this. So what it says is like as your flow rate increases, your percentage conversion decreases, and it also follows something like an exponential trend. So this is a this will be one of the result from your process simulation. So so this is so that's how we build. So for the if you take an Aspen HYSYS, you can you can you can simulate a CSTR. You can drag and drop a CSTR unit. You put some input, and then you give the right amount of right information to the input. Like this is the pressure, that's the temperature, that's my fluid. These are the two types of fluid that goes in. That's my reaction kinetics, and then we can ask the software to solve. Okay, I want something like a volume as a function of conversion, or like a flow rate versus conversion. So it can do it for you. So this is another thing that we can do. So for the same problem, now I want to change the volume and I fixed the flow rate to 100 milliliters per minute. And now I want to know how my percentage conversion changes with respect to volume. So if your volume increases, your percentage conversion should increase. The trend should go like that. So ignore the red line. So this is the correct line. Your percentage conversion will increase with volume. Why is that? Because your residence time increases. This is another thing. So here I just plotted residence time directly in the x-axis and then percentage conversion. So this is something like a process simulation. So if you are simulating the the CSTR tank, and then we are just looking at the different trend. So if my residence time increases, the percentage conversion is going to increase. So these are the things that we need to do. And this is a I put the formula here. This is a very useful formula when we are going to use Aspen HYSYS. So take a note of this residence time. If you know the volume, if you know the flow rate, you take the ratio that should give your residence time. And if you want, you can even solve the unit. So volume, if we express it in liters, let me change back to pen, liters, and then flow rate, say like liters per minute. So liter will get cancelled. You will get some unit that in time units. So that's your residence time. So in Aspen HYSYS, we call them as a case study, like these three graphs which I showed you, like residence time versus conversion, like this graph, volume versus conversion, and also the graph which I showed in the previous page, this one, like a flow rate versus conversion. All these things, these are like a case studies. So you're you're just simulating the whole process. You're just changing the operating variables, like your flow rate, your volume, and then your residence time, and then we are changing. We're checking how the percentage conversion changes. Yeah. So obviously, if you change the volume, obviously it's going to change the residence time. If you change the flow rate, obviously it's going to change your residence time. Yeah. So that's the thing you should remember. Yeah. So that's what the process simulation is all about. So what we are giving is, let's go back here. So we are giving some inputs, we are getting some outputs. In this case, some percentage conversion, and then we are giving some inputs. We will explain what are the inputs that we need to give. What I wrote here is like, to get that output percentage conversion correctly, we need to supply few more information. Yeah. So it's not like that. Okay, I know how to draw a CSTR tank, and I know how to draw two arrows where I can put A comma B. That's my reactant, and I know where the product comes out. That's not enough to get the percentage conversion. You need to to work a bit more in order to get your percentage conversion as a function of your operating variable. So to set the, it's I think I said already. So clearly there is some chemical reaction. So that's why there is some bond breakage is happening. That's why you get some new products from your reactants. And then obviously your percentage conversion is going to change with the residence time. The general rule is like a percentage conversion is proportional to your residence time. So it means you need to know, or you need to know what type of chemical reaction, and then you need to know the reaction kinetics involved, and we have to supply the reaction kinetics to the software. Only then it will do the job. It can predict your output correctly. Yeah? So we need to give this information, reaction kinetics, and then so this reaction kinetics, it will tell percentage conversion, and it also will tell how fast your reactants are getting converted into your products. Yeah? So this is obviously reflected in percentage kinetics. Yeah. And then so go back to highlighter. So just I'm going to box it. So this is one of your input, reaction kinetics. That's one of your input. Also we need to know we know that reaction kinetics increases with temperature, or is a function of temperature. Definitely, normally mostly it follows this Arrhenius type expression. And then so whenever I say reaction kinetics, so how it may look like, it may look like that. So this is your rate expression. You have some constant k1 k2, some exponent, and then one of your kinetic constant is proportional to, sorry, is follows this Arrhenius expression. Yeah? So k is equal to exponential of your activation energy divided by the gas constant multiplied by the temperature. So something like this. So this is some equation, some expression that we need to supply. Only then it will correctly calculate your output for the given set of inputs. Or your expression may look even more simple like this. K as a function of Ca raised to the power of n. Again, it can follow some Arrhenius expression, your something like that. And then another thing we need. So that's one input. Another thing is reaction stoichiometry. So 1 mole of A reacts with 1 mole of B, that's to give 1 mole of C. So we need this information. This is another input, and we also need to know which one is the limiting reactant. And sometimes we may need to supply one reactant in excess in order to get in order to convert all of your reactants into products. So we need to know those type of informations as well. So this is another input, your reaction stoichiometry, and obviously the number of components involved in the reaction. This is A, B, C. All these are inputs. And then process conditions. Obviously, there are some reactions you can perform. Obviously, you can perform reactions at different temperature and pressure. So you need to know whether you are performing a reaction at atmospheric pressure or at a higher pressure, or and also temperature, what at room temperature or at some elevated temperature or at cryogenic temperatures. So you should also give information of your process conditions. So these are some precise information that we need to supply, and only then we can successfully simulate the whole process, and then you can get your percentage conversion as a function of your process variables. And uh, and also we need some mathematical expressions, so or a model, if you want, we can call, that can accurately predict your fluid properties. So what is this A, B, and C? So A is not a, it's like a just a just a notation. A is some fluid, it has to have some particular properties, and B is some fluid, it has to have some particular property, and C is some component, it has to have some particular property. Yeah? So we need to have some expression that allows to accurately predict the fluid properties. Yeah? Say like a, let me come back to the pen. Say like I have some function y is equal to fx. Let's say this is the simplest mathematical model, and this model should predict accurately the fluid properties of A. So if I substitute some, okay, if I give some values, this model should tell me, okay, this particular component A is gas at that particular temperature. If I change the temperature to cryogenic temperature, it should tell, oh, this component at this particular temperature it will become liquid. At that particular temperature, this component will start to boil. So it's you need some mathematical model that should accurately predict the fluid properties. Like it should predict its, for example, its boiling point, freezing point, and so on. Yeah. So these are the things that we also need a suitable mathematical model, but don't get scared of this. The software already have a lot of models. We call them as a fluid package. So we can select one of them. So it's so you don't have to worry about this. Don't think like we are going to do some heavy duty mathematics in order to predict the fluid properties correctly. So we have a lot of equation of state and other models that allows you to predict the fluid properties precisely. Yeah, so I think so far so good. Mm, I'm using a very small tab to record this video. Most of the time it will crash. So I'm going to save until now, and then I'll continue immediately.